Okay, we want to continue on talking about dynamic finite element modeling. And I've already, in previous lectures, not so much in this chapter, but when we were talking about explicit integration, both in 3D and in 1D, I've already shown you the explicit technique. So what I want to talk about in this lecture is called the Newmark beta implicit integration method. So let me begin talking about how we're going to develop this by just recalling the discretized equations of motion, right? And those equations, remember, this is still, we're in the linear elastic case. So it's like m times u double dot, the acceleration, the nodal acceleration vector, which can be a function of time. So m times u double dot plus k, the stiffness matrix, times u, which also could be a function of t, is going to be equal to some reaction vector r, function of t. Okay, let's call that equation 1. Okay, we've already shown how to solve these equations with an explicit central difference approach. And so here what we want to do is we're going to develop the traditional implicit integration method called the Newmark beta method. Okay, so we're gonna derive this essentially. So if you remember a little bit from maybe a numerical methods class, you remember that an explicit approach, we're just going to take everything from the previous time step and then push it forward into the next. In an implicit approach, we're going to write sort of our equations with a component from the previous time step and a component from the current time step, and then try to solve out what the equations would look like for the current time step that we care about. So we're going to start by, to develop this method, we're going to start by just expanding the velocity at some increment k plus 1. We're going to use a first order expansion and then invoke the Taylor theorem. So let's write that down. We're going to first expand the velocity at the k plus 1 increment in a first order Taylor expansion. So we develop this by first expanding the velocity at the k plus 1 increment in a first order Taylor expansion, and then we're going to invoke Taylor's theorem. Okay, so what does this look like? So let's write down first, we have u, this is the velocity, so this is u dot at k plus 1 increment. What's the Taylor expansion of this? Well, it looks like u dot at the k increment, okay? Plus, this is a first order, so we just have delta t times u double dot evaluated at tau, okay? Now you might be thinking, wait a second, what is this about? Shouldn't this be u double dot evaluated at k? Well, I didn't write approximately equal to, I wrote equal to. And this is what I mean by invoking Taylor's formula, or Taylor's theorem rather. Taylor's theorem said this is exact, provided that tau is somewhere between the time value at the kth time and the time value at the k plus 1 time. Okay? So let's call this equation 2. So this isn't an approximation, this is actually equal. Okay? So now I'm going to go ahead and write this u double dot tau as a linear combination of the acceleration at time tk and the acceleration at time tk plus 1. Okay? Okay, so what does that look like? Well, what we're going to say is that u double dot of tau is going to be equal to, we'll call it gamma. This is just a constant, or a weight, this is going to be a weight factor, a weight coefficient, but you'll see how it works here in a second. U double dot of k plus 1 plus 1 minus gamma of u double dot k. Okay? So that seems relatively easy. Let's call this equation 3. And you can kind of see what's happening. Gamma is just controlling. So if gamma starts out at 0, let's say, then we're in a fully explicit form where we only care about the previous acceleration. If gamma is equal to 1, then we're basically saying that u double dot is whatever the value is at the increment we care about. And if it's in between there, then it's just some weighting in between them, okay? So let me define that. Where gamma is some weight between 0 and 1 that gives basically the weight of the u double dot k plus 1 term. So now we're going to substitute equation 3 into equation 2. And we have that u dot at k plus 1 is equal to u dot of k plus delta t, and then times what we had in equation 3, which is gamma u double dot k plus 1 plus 1 minus gamma u double dot k. Okay, let's go ahead and call that equation 4. So next, we're going to take the displacement at u of k plus 1. We're going to expand it in a second order Taylor series, and then invoke Taylor's theorem again. So when we do that, we have that u of k plus 1 is going to be equal to, of course, u of k, right? And then our first order term, which will be plus delta t times u dot of evaluated u dot of k. And then plus, now we have delta t, the quantity squared, over 2. And now we're going to invoke Taylor's formula. And so this becomes u double dot tau. I'm going to put a hat over it so that you know it's not the same tau necessarily as what was in equation 2. Okay? But it has the same definition, right? Tau hat is between tk and tk plus 1. Okay, let's call that equation 5. We're going to do the same thing. We're going to write u double dot of tau hat as a linear combination. Instead of gamma now, we're going to call the weight 2 times beta. We gives the following, right? We have that u double dot of tau hat is equal to 2 beta u double dot k plus 1 plus 1 minus 2 beta times u double dot k. Let's call that equation 6. So now we're going to substitute 6 into 5. And when we do that, we can then write that u of k plus 1 is equal to u of k plus delta t times u dot of k, right? Plus delta t squared over 2 times the quantity 2 beta u double dot k plus 1 plus 1 minus 2 beta times u double dot k. Okay? Let's call that equation 7. So now let's go ahead. What we're going to do is we're going to solve equation 7 for u double dot k plus 1. And when we do that, we have that this is just an algebraic exercise. U double dot of k plus 1, that equals 1 over beta times the quantity delta t squared, okay, times u of k plus 1 minus u of k minus delta t times u dot of k, okay, and then minus 1 minus 2 beta divided by 2 beta times u double dot k. Okay, let's call that equation 8. So now what we want to do is substitute equation 8 into equation 4. So that's going to give us that we have u dot of k plus 1 is equal to u dot of k plus, now we have gamma over beta delta t times the quantity u of k plus 1 minus u of k minus delta t times u dot of k, okay, minus gamma delta t times 1 minus 2 beta over 2 beta times u double dot k, right, plus delta t times 1 minus gamma times u double dot k. Okay, we can simplify this, as you might expect. And if we simplify it, it comes out to, we can pull this out, say this is gamma over beta delta t times the quantity u of k plus 1 minus u of k. Okay, and then plus 1 minus gamma over beta delta t times u dot k, okay, plus delta t times the quantity 1 minus gamma over 2 beta times u double dot k. Let's call that equation 9. Okay, so we're going to come back to these. This is the form that we're going to ultimately need, but let's go back to equation 1 actually and write what the equation would be in an incremental sense. So here we go, rewrite equation 1 in incremental form. Okay, so when we do that, we have that m, right, that doesn't change, but we would say that u double dot of k plus 1, if that's the quantity of interest, then plus k times u of k plus 1 must be equal to r of k plus 1, right? This is straightforward. Let's call that equation 10. Now what I want to do is I want to substitute equation 8 right up here into equation 10. Okay, so I have this mass matrix out front, and then I just drop the entire equation 8 into here, which looks like 1 over beta delta t squared times uk plus 1 minus uk minus delta t times uk dot, right? And then we have this minus 1 minus 2 beta over 2 beta times u dot double dot k. Okay, so that whole thing, and then we have the plus k times u of k plus 1 equals r of k plus 1. Right? So that's the starting point. Let me do some grouping of terms. So if I group my terms, I can factor out uk plus 1. So let's do that. So I have this first term here, so I'll have the 1 over beta delta t, the quantity squared, times my mass matrix M. And then I have another term over here, so I have a plus k, that quantity times u of k plus 1. Okay, and you'll see the rest of my terms are all negative, so I'm going to go ahead and write an equal sign there. Say that this now equals r of k plus 1. I'm going to bring all these terms to the other side. So this will be plus the mass matrix M times the quantity 1 over beta delta t, the quantity squared, times uk plus delta t uk dot, plus then this factor here, 1 minus 2 beta over 2 beta times uk double dot, parenthesis around that. Let's call that thing, let's call that equation 11. Now I want to solve equation 11 for uk plus 1. I can write then that u of k plus 1 must just be this matrix quantity inverted. So 1 over beta delta t, the quantity squared, times m plus k inverse, and then times this whole thing, right? So times r k plus 1 plus m times this quantity that we just wrote down. 1 over beta delta t squared times uk plus delta t times uk dot, right, plus 1 minus 2 beta over 2 beta times uk double dot. Okay, and then we'll go ahead and close these brackets here. Let's call that equation 12. So let's look at this. So what can we observe here? Well, if I look here, everything on the right-hand side of equation 12, except for this force vector, is related to the previous time step. So if I have a new force vector at the time step k plus 1, then basically the first thing I'll do is update to get the new displacement uk plus 1. Okay? So we only have, so observe that the new force vector is the only k plus 1 quantity on the right-hand side. Okay, so what that means is that we can first, the first thing we'll do in our analysis at every step is going to solve for uk plus 1. Okay, so once we have that, now we have uk plus 1, then we can go ahead and solve for u double dot of k plus 1 using equation 8. Once you have that, then you're gonna solve for u dot k plus 1 using equation 4. Okay? So why do we use this method? Well, the primary reason is that it can be shown that this method is unconditionally stable for the following. In the case where 2 beta is greater than or equal to gamma and gamma is greater than or equal to 1/2. Okay, let's call that equation 13. Okay, what does unconditionally stable mean? So it's an important quantity, right? It's something that that we don't always get with explicit solutions, right? We don't get with explicit solutions. So what does this mean? What is an unconditionally stable solution? It means that the solution does not diverge or blow up no matter what we choose for delta t. Except that it should be noted that if you change delta t, if you make it large, you can degrade your accuracy, but it doesn't make your solution blow up. So how do we know what values we should choose for gamma and beta? Let me give you some remarks to tell you. Okay, number 1. So there are several commonly used versions of this method. All of them have unconditional stability. Okay, so the most commonly used one is what's called the average acceleration method. Okay, and in that method, you're going to set gamma equal to 1/2 and beta equal to 1/4. Okay. The error in this case is going to be something that's the order of delta t squared. Okay? Sometimes when you run dynamic analyses, what you're going to want to do is you're going to want to damp out vibration modes that may not be physical. So you want to, and usually those are particularly relevant in high frequency. You don't usually want to damp out low frequency, but you want to damp out high frequency. So as a result, it's convenient to introduce some level of damping to knock out those unphysical modes. And so this can be done with the beta Newmark method. It's called an algorithmic damping. So we can, this is the next option that I'll tell you. This is called algorithmic damping. Okay, and this happens anytime you have gamma that's going to be greater than 1/2, right? And then you'll have beta be greater than the quantity gamma plus 1/2, the quantity squared, over 4. This will be greater than or equal to. Okay? So that's great. In the algorithmic damping, it's going to damp out some of the modes. We have a disadvantage here in that the error is not as good. So in this case, the error is of order only delta t. Okay? Maybe you're not used to looking at these. What this means is that if delta t is small and I make it, let's say, half as small as it was before, then I get roughly a factor of 4 improvement in my error, whereas here it just scales linearly. So you want your error to be as high as possible in terms of the order on delta t on the delta t term. Okay, and then a method that is worth noting also is called the alpha method. This is sometimes called the Hilbert-Hughes-Taylor method, and in this case we say that gamma is equal to 1/2 times 1 minus 2 alpha, and then beta is equal to 1/4 times 1 minus alpha squared. And in this case, alpha is going to be less than 0, less than or equal to 0, and greater than or equal to -1/3. Okay? And the advantage to this method is that it gives you some damping like the algorithmic damping, but your error is better. So this has an error of just like we had with part A, of delta t squared. Okay, so the advantage of this method is that it introduces algorithmic damping with only an order delta t squared error, which is good. Okay, number 2. This is really just what I stated before, but damping is introduced for gamma greater than 1/2. Which is often desirable to damp out unphysical higher frequency modes. But I will say this is typically at the cost of accuracy. Okay, number 3 follows on what I also had said about the alpha method, right? It introduces less damping in the lower modes, and you want those lower modes to be more accurate, which is going to preserve their accuracy and is going to ultimately lead to a lower error. Okay? The last thing I want to say is about something called operator splitting. Sometimes it's appropriate to use different kinds of integration in the same problem. So you might want to use implicit integration for one part of the problem and explicit integration for the other. And an example of this would be maybe in a fluid structure interaction problem. Okay? Whenever we do this, whenever we have part of the problem with implicit and part with explicit, this is called operator splitting. Or sometimes just mixed time integration. Okay? So that sort of covers the development of this implicit method. So now you have in your toolbox, hopefully, an explicit method and now an implicit method for solving. And you know how to go about solving both of those. So hopefully that gives you the tools that you need to solve really any sort of dynamic problem that you're going to come across.